Alright guys, so we want to go through the Hopkinson test or the Hopkinson method. The purpose of this calculation is for us to be able to know how to calculate efficiency in a generator and a motor. And as an introduction, we're going to go through how to sketch the circuit. So for the circuit, this whole calculation revolves around this very circuit here. So this circuit typically it has two armature resistors. It has two armatures. So it has one which is on the side for the generator, and you have the other one which is on the side of the armature. The motor, sorry. So one refers to the generator, the other refers to the one for the motor. So this side, the one I'm sketching right now, it's for the motor. I'll add labels in a moment. And then this one, let's do this. So this side is for the generator. The other side is for the motor. We'll just move our armature there. Good. So we have our two armatures. Let's label them. So we're saying this one on the left hand side is for our motor. This one is for our generator. Now both of these armatures then are connected in parallel to two field resistors. So this side I'm going to have a field resistor connected in parallel with my motor armature. On the other side I have my field resistance connected in parallel to my generator. Now when you go about this calculation, and especially for the method I am showing you guys, it's easier for you to go through the calculation if you know the circuit. It makes things easier. Sharp. So let's go through labeling then. Here is where we're going to have our terminal voltage or supply voltage. Here we said we have a field resistance, we have another field resistance. So this is our motor armature resistance, this is our generator armature resistance. Now starting here, the actual calculation revolves around a couple of currents we have throughout the whole circuit. So these arrows represent those very currents. So starting here, we have our terminal voltage or supply voltage. We have a current which comes from the supply voltage or the input voltage. This current typically is labeled as I2. So now the mission is to make sure we know all the names of the currents we have throughout the whole circuit. So I2 then will be referred to, I2 then is referred to as the input current from the mains. Yeah, so that's our I2. Let's write down that properly. So we have our input current from the mains, current from the mains. Current is measured in amps. Since the main supply is this side, you have I2 referring to input current from the mains or the main supply. Sure. Now let's deal with the current which will pass through the field resistors. We have a current which would pass through this RF, and we have another current which would pass through this one. So because you have your motor armature here, when they refer to the current which will pass through the field, the reference will start from the motor side to say they'll make a reference to a motor. So thus they'll say the motor, then they'll refer to the field to say that this current should be passing through the field. So thus they'll say motor field current, since it's passing through the field resistance on the motor side. When they label this one, it's labeled as the symbol I4. So this side we have I4. Now we need the current which will pass through the field for the generator side. So in the same principle, they refer to I4 as motor field current. The one through the generator side, they'll say the generator. They refer to the field resistance, then they say the current there. So generator field current, then in our case, it's going to be I3. It's going to be I3. We're going to have I3. So that's our generator field. So far we have I4. I4, we know it as the motor field current. And then we said I3 is the generator field, since it's on the generator side, current measured in amps. Sharp. Now you'll notice before we deal with this one and that one, there's another one we have here. So you'll notice there's an arrow which is moving out of the side of our generator armature side. So we have one current which is moving out of the side. So this current, then the symbol for it is I1. So when they refer to I1, then they say I1 is the generator output current. Generator output current. Output current. It's also measured in amps. So because I1, the arrow is moving out of the side of the generator, you have I1 as generator output current. Now you'll notice from this junction here, technically you have I1 goes that direction and you have I3. So the current that broke here is the same as I1 plus I3. So let's go through it again. So I'm saying we have this arrow pointing upwards here. It means as soon as it reached this junction, the current split. Some current went that direction, another one went up there. So thus I'm referring to I1 to say I1 already comes from this place. I3 as well comes from this same area here. So thus we can say the current you have here is the same as I1 plus I3. So then, considering that this same current must have passed through the generator armature resistance there, then we then say I1 plus I3 is then referred to as the generator armature current. You have I1 plus I3 as the generator armature current. At this junction, you have I2 and I1. They meet at this junction. When they meet here, they go downwards. And so they should add since they meet at this junction. So thus you have I1 plus I2. At this junction, you already have I4 moving away from this section here while you have this arrow moving downwards. So thus you can represent that as I1 plus I2. Because I4 is moving away instead of towards this point moving downwards, you say minus I4. So this very current I1 plus I2 minus I4 is the same current which will pass through the motor armature resistance. So thus we have I1 plus I2 minus I4. So since it's passing through the motor armature, in this case this is going to be our motor armature current measured in amps. So these are our currents. We need to make sure we know all of these symbols. This calculation is very friendly if you know the name of your symbols. So moving from these is then our equations. So I'm not going to take you through the method they use in your textbooks. The method they use in your textbooks, it's very much the same as this one, except for I'll be honest, this is a very lazy method. and maybe I should say it's dangerous, and later on I'll explain why. So for the equations, because I'm not committed, I'll take you straight to the formula sheet. So formula sheet, there. We have equations there. So now for our equations, on the formula sheet, whoever wrote the formula sheet for Electro N6 probably said, I don't trust these people, so let me write the topics next to them. So there, Hopkinson, can you see that? Hopkinson efficiencies. So there, for the Hopkinson method, they decided to give us the formulas. So now, these formulas come in two forms. The first formula we have is this one. We have this equation here. And so for this formula, there's a condition, and fortunately they have written it for us on the side. The condition for this one, here is the name of the condition. And so our condition, just to show you, is written exactly here, but it might not be clear. So for the purpose of clarity, just to make sure that we don't do any mistakes, when you use this formula, you will read a question, it will say calculate the efficiency if you have equal or the same efficiencies either in a generator or in a motor. Your actual condition is this very one here. You read the question and it says calculate the efficiency for the same or equal efficiencies. If they happen to mention such a condition as this one, you know you use the formula efficiency equals to the square root of I1 over I1 plus I2. This equation, we use it at N3 for the same calculation, except for this is the only condition which is there at N3. But at N6, this is one of the conditions for the Hopkinson test or method. So you use this formula here. The second condition is then written for us here. So for the second condition, it's written here. And the formula for the formulas for the second condition are all of these here. So like I'm saying we have two conditions. The first one says equal or the same efficiencies. The next condition then says for equal I'm lying, it doesn't say equal. What does that condition say? Let's check some questions. Maybe they'll remind me here. Yeah, equal, yes. So I'm right. I know I cheated, but it's part of life. So yeah. So we have equal or the same friction and windage losses. In this case, it can also be referred to as equal iron and friction losses. Actually, that's how they typically write it. Let's write it as equal iron and friction losses. Now, for this condition, the first step always, step number one, always, depending on that machine, if it's a generator or a motor, is to calculate for C. So this whole formula here refers to C, how to find C, where you'll substitute all those currents which we were discussing right now. All of these, the purpose is to assist us to find C. After you find C, When they say calculate the efficiency for equal iron and friction losses for a generator or a motor, then in such a case you will see whether if it's a generator you're using this one, if it's a motor you're using the next equation. At the end you just need to remember that you need to multiply both of these efficiencies by 100% as it is standard. Now you'll notice that in the formulas that there's a C over 2. So thus, after you find your C value, at least make sure you divide it by 2 so that you can substitute it there as a final value. Now, like I'm telling you guys, this is a very lazy method. There's a very proper method. Well, yeah, there's this proper method in your textbooks, and that method assists you to find these different losses. So we have a loss here as our input, there's a loss here, there's a loss there, there's a loss. Yeah, so when you use that method, the alternative, yeah, there are people who've already shown you guys that method. This one is a very older method. So yeah, so someone will tell you this method is dangerous. So the only reason why I will tell you it's dangerous, it's because you literally substitute your information throughout the equation, and your actual danger is during substitution wise. So that's where we have actual issues around this calculation, the danger of substituting across the whole equation there. So you guys can go through the alternative method in your textbooks. I'm going to show you this dangerous one. Why? Because I'm lazy. Are we okay then? And I like working hard. Well, yeah, but use the best method you prefer, either the one in your textbooks or you can use this one. So to go about this calculation, maybe let's try one question or two. I'll actually do 2 questions for this one. Yeah, let's start with the first one here. So we're going to try to do this first question here. Let's throw it in here. All right. Sure. So the question says 2 similar DC shunt machines were tested by means of the Hopkinson method. The following readings were obtained. The terminal voltage of each machine. So they gave us V. We can collect our data. I'm just going to write it next to these given data. So there we have V. The armature circuit resistance of each machine, we have RA. The generator output current. So now we're going into those currents. So our generator output current, we established that it is the current which is moving out or moving away from the side of the generator. The only current we have is I1. So our generator output current here, we have I1. Okay, we have the input current from the mains. Input current from the mains, our main supply is this one. So input current from the mains, in our case, it's I2. And then the motor field current. Motor field. So you remember they refer to the motor, then field, the current that should pass through the field. In our case, it's I4. So there we have I4. Then lastly, we have the generator field. The current, I3. So we have I3 there. Then the question says, calculate the efficiency of the machine operating as a motor, assuming equal iron and friction losses. Assuming equal iron and friction losses. So assuming equal iron and friction losses for our equations, we go into the iron loss section. Assuming equal iron and friction losses. So did they tell us the machine? Let's check the question. Calculate the efficiency of the machine operating as a motor. So we're going to be looking for our efficiency operating as a motor assuming equal iron and friction losses. So assuming equal iron and friction losses, our equation, we will be using this second one, the one for efficiency, as a motto. But we know before we go through this, we first have to find the formula for C. We have to use the formula for C. So to use the formula for C, let me just borrow these formulas quickly. So the formula for C, that's going to be where we will be starting with our calculation. Okay, let's crop this because we're starting with the formula for C. Sorry guys. So to find the formula for C, let's go sharp. I'm going to rewrite it so that I pretend I'm dedicated. So this is going to be C equals to I2 times V minus, and there we have I1 plus I3 squared RA plus we have I1 plus I2 minus I4 squared RA plus I3 plus I4 times voltage there. Let me get rid of this. Sure. So there we have our formula for C, and we want to substitute. So to substitute, let's substitute then. So for our C, I2, they gave us, we have 400 times our terminal voltage, which is 600, minus open bracket, open bracket. Our I1, we have 1200 plus I3, we have 25 square times our RA, say times 20, RA we have 0,05 plus in here our I1 we have 1200 I2, okay, 400 minus 20 squared times 0,05 plus our I3 we have 25 I4 plus 20 times 600 there. So the first danger is you substituting apples here. If you find yourself substituting carrots here, then you'll definitely make a mistake somewhere. So let's substitute then. So we have 400 times 600 minus open bracket 1200 plus 25 close bracket squared plus open bracket 1200 plus 400 minus 20 close bracket squared times 8 times 0,05 plus 25 plus 20 times 600 close bracket. Hopefully I didn't do a mistake. Yeah. So only because I know the answer, I'm gonna retype and check if I didn't do any mistake. Let's check if we didn't do any mistake. We have 400 times 600, 1200. We forgot to multiply 0,05 to this section here. So that's part of the dangers of this method, and fortunately you guys are seeing it firsthand. Let's see if yebo, that's our answer. I am getting this value 13148.75. So for safety purposes, make sure at least you type your value 3 times or 2 times, just for safety purposes. Then we know we want to find C over 2. So your C over 2, you can divide this value by 2. So in this case, this is going to be divided by 2. And our answer, we are getting 6574,375 watts. So our C value, these constant losses are power values, so they're measured in watts. So here we have 6574,375 watts. Next part of the calculation, efficiency. So for efficiency, remember we're doing efficiency measured as a motor for our machine if it's operating as a motor. So if we have for efficiency running as a motor, I'm going to rewrite this formula. So let's go through it. So efficiency as a motor, we have I1 plus I2 minus, this is I1 plus I2 minus I4 squared RA plus I4 times V plus C over 2 all over, this is all over our I1 plus I2 times V times 100%. So that's our equation. Let's get rid of this one. Sorry. So we want to substitute then. So let's take this. So to substitute, let's see then. How much is our I1? I1, we have 1,200. 1,200 plus I2. I2 we have 400. What else do we have? Our voltage at the top, it was 600. So it's 600 minus open bracket. Our I1, we still have 1,200 plus, this is 400 minus our I4, which is 20 squared times 0,05 plus our I4, we have 20 times our V was 600. Let's confirm. There it is at the top, 600 plus, earlier we found our C over 2, we have 6574,375, close bracket. And you have all of this divided by our I1 plus I2 hopefully I wrote this formula correctly. This is 1200 plus 400 times 600. So the danger, like I was telling you, within this formula is making mistakes. So we have 1200 plus 400 times 600 minus open bracket, our I1, we have 1200 plus 400 minus 20 all squared times 0.05 plus 20 times 600 plus 6574.375 close bracket. Hopefully I didn't do any mistake. We have at the bottom 1200 plus 400 times 600 equals to this times 100, and that's our efficiency. Our efficiency, we are getting 85,063 85 comma how much? 063 percent times 100%. So that's how you go about this specific question we were doing. I hope it makes sense. Maybe let's try do another calculation. Let's try do the second one. So as long as we know our symbols, we are safe. All right. We're doing the second question here. Let's copy it. All right. So for our next question, let's see what do we have there. Alright, so it says the following results were obtained in a Hopkinson test on 2 shunt machines. Supply voltage, the given one, so supply voltage is our terminal voltage. So we'll do as the previous one, we have our V. Generator armature current, generator armature. So armature current, let's check our generator armature currents. Generator armature current, we spoke of this current which passes through the generator armature resistance. In our case, it's I1 plus I3. So in this case here, we have I1 plus I3. Next, we have the motor armature current. Motor armature current is the one which should pass through the motor armature resistance. In our case, it's I1 plus I2 minus I4. I1 plus I2 minus I4. I1 plus I2 I1 plus I2, I2 minus I4. Then we have our motor field current, and motor field, let's go, I4. We have I4 motor field current, I4. Yeah, I4. And then generator field, let's go back to our circuit, generator field current, I3. We have I3, generator field current, we have I3. Then armature resistance off. Yeah, this was a typo here of each machine. So here we have RA. There. We've covered our data. Question says calculate the efficiency of the machine acting as a generator. So for this calculation, our machine will be acting as a generator, assuming each of the following. The first condition says for equal iron and friction losses. The second condition then says for equal efficiencies. So first thing is it's operating as a generator if it has equal iron and friction losses across both the generator and a motor. So equal iron, well, no. In our case, we're just looking for it as a generator. So we go to our formula sheet. So in this case, we will be dealing with this formula. For now, maybe let's start finding C. Okay, so because I'm not so committed, let's just copy C from the previous calculation. Hopefully we can do that. So here's our formula for C. Let's see. C. So we enter in 2.1. 2.1. Impress me. Ha! I'm a genius. So our first step is to first find C. After we find C, we want to substitute it into the formula for efficiency of a generator. So later on we'll copy this formula again, rewrite it. So since we're looking for C, let's substitute then. So equal iron and friction losses. First step, first find C. Second step, find your efficiency for that machine. So our I2, now you will then notice for this method, we don't have I2. So we then need to work on finding I2. Do we have I? Yeah, so let's work on finding I2. So you'll notice the way they gave us this data, they gave us in such a way that we have I1 plus I3, I1 plus I2 minus I4. They gave us I4 and I3. So we actually don't have I1. We also don't have I2. So as a first step then, before we actually go into the question itself, which the marks are located for it, our first step is to find those two currents. So you'll notice then the formula for I1 plus I3, we have I1 plus I3. Also they gave us I3. So what you then do is this, you can find I1. So here, this is what I'm talking about. Let me show you. Just around there, they gave us I1 plus I3, and here, maybe let me use a different color marker so that you can follow along. So I'm talking about this. Yo, can you guys see that color there? Alright, I'm talking about this and that. We're going to use that two information. So in our case, we have I1 plus I3 is equals to how much? 35. Then again, they already gave us I3. So I1 plus I3, which is 0,9 equals to 35. You want to find I1 is equals to, you subtract the other side, you're saying 35 minus 0,9, and we're getting 34,1. 34,1 amps. We found I1. You still want to find I2. To find I2, this time you are using this one. You're using that formula. You have everything else. They already gave us I4. In fact, let's highlight our I4. Here, we have our I4 there. So, if that's the information we are using, then we're saying I1 plus I2 minus I4 equals to 45. Fortunately, we just found I1. We are looking for I2. So our I2, oh, let's substitute first. So our I1, we have 34,1 plus, we're looking for I2 minus our I4, which is 0,8 equals to 45. So from here, I'm just going to be transposing. So we're going to have 45 minus 34,1. If I transpose this 8 to the other side, it's going to add. So it's going to be plus 0,8. And we are getting how much? 11,7. So for our I2, we're getting 11,7 amps. There. From here, let's now find our I2. So for our I2, we have 11. Let me just be safe. 11,7 times our voltage. They gave us a voltage of 415. 415 minus open bracket, our I1 we have. Now, there's some steps which we can jump like this one. Instead of substituting I1 plus I3, fortunately they already gave us I1 plus I3 there. It's 35. So in here, you can just say 35 squared times 0, how much is our resistance? 0,5. There. They gave us I1 plus I3 at this step here. I1 plus I3. So we don't have to substitute I1 plus I3 as a whole value, like substituting your I1 34,1 plus the I3 value. So I hope that makes sense. Here also we have I1 plus I2 minus I4, which is the same as the generator armature current. We have 45. So in here you can still say 45 squared times our resistance, we have 0,5 plus I3 plus I4, we have both those values. For our I3 we have 0,9 plus I4 we have 0,8 times our voltage, which is 415, close bracket. So there, this is the simplest method for substitution. If you feel your name is called dedication and passion, then oshine and substitute these guys. Maybe someone will pay you for that. So yeah, otherwise this is the alternative method for substitution. Let's move on quickly. 815. So for substitution wise, we have 11,7 times 415 minus open bracket, we have 35 close squared 2 times 0,5 plus 45 squared close times 0,5 plus 0,9 plus 0,8 times 415 close bracket. I hope I won't do a mistake. I hope that's the correct answer. 2525 watts. Let's find our C over 2. We're just going to divide that value by 2, divide by 2, and we are getting 1262,5. 1262,5 watts. We divided that value by 2. 1262 divided by 5. 2525 divided by 2. Next, we want to substitute it to our formula for efficiency. Our formula for efficiency, we are using the one as a generator. So let's copy this formula here. So I'll take you through the mark allocation. Hopefully I'll give you the right one. I'm rewriting this formula. Efficiency as a generator, we have I1 times V over, we have I1 times V plus I1 plus I3 squared plus I3 plus C over 2 times 100%. We substitute our information. So I1 we found it at the beginning, we have 34,1. 34,1 times our voltage, it was how much? 415, I think. Here's our voltage, 415. 415 over all over 34,1 times 415. So we have I1 plus I3. You remember it was given to us at the beginning. I1 plus I3 here is 35. So 35 squared, our RA, I forgot to write it. Here it is, 0,5. And then our I3, let's check I3, we have how much? 0,9. 0,9 times 415. Our C value, C over 2, we have 12, 62,5 times 100. And then let's pray in tongues, we won't do any mistake. So let's go. 34,1 times 415 over 34,1 times 415 plus 35 squared times 0,5 plus 0,9 times 415 times 100. We have 93,486. I hope we didn't do any mistake. 486, 486%. Let's just check if we didn't do any mistake. So at the top on our calculator here, we have, let's take this up, we have 34,1 times 413. At the bottom, 34,1 times 413, we have 35,5 plus 0,9 times 415. Hey, we forgot to add 1262,5, and that's why we don't recommend this method, because we're likely to do a mistake. So please don't try it at home or in the exam. Follow your hearts. You can use this method, it works. So alternatively, you can use the other one. Yeah, so at least you guys are seeing mistakes done immediately. So make sure you confirm your work at least 86,29. 86,29. Sharp. If there's anything I haven't covered, is mark allocation. So mark allocation, typically for this one, usually this calculation is about 11, 12 marks or so. So they should give you a mark for each loss. So there, 1, 2, maybe 3, 4, 5, 6, 7, 8, let's see, 9, 10, 11. Yeah, 11 marks is around there. 9 to 11 marks, 12 marks. Your 13, I'm not sure, but there's an allocation sometimes for finding those first two currents there. But 13 is too much. So typically, like I'm saying, about 11 or so marks for this very calculation. So remember, we were looking for efficiency for the first condition, equal ion and friction losses. The second one, 2.2, it says for equal efficiencies. For equal efficiencies, we're using the second formula. Let's go to our, we're using, well, the first one, this one. So this one, it's easy to remember. So let's write it as it is. So equal efficiencies, we are saying 2.2 efficiency equals to the square root of I1 over I1 plus I2. This one is for around 2 marks. So I1, our I1, we got how much? 34,1. So we have 34,1 over 34,1 plus, how much is our I2? I2, here's our I2, 11,7. 11,7. And then let's substitute mothers and fathers. 34,1 over 34,1 plus 11,7. Is it 11,7? And this one. Yeah. And we are getting similar efficiencies here. Well, hopefully we didn't do any mistake. 87,287. 86, that is. This is times 100% times 100%. I got 86, 2 what? Let's see, 287. 87%, and this is percent. And so this is how you go about this calculation. So your responsibility is to at least, well, firstly, before you go into the equations, you make sure you know your diagram. You make sure you know how to sketch this diagram, how to label it correctly. Let's go through it quickly. So we have current from the input or the supply, or from the input current from the mains or the input or the supply, I2. You have motor field, I4, motor field current, I4. You have generator, you refer to the generator, you refer to the field resistance current. The current is passing through the generator field resistance side of the circuit, current, I3. You have one current moving out or away of the side of the generator, which is I1. And then generator armature current, I1 plus I3, the one which split at this point. And then you have motor armature current. They haven't asked this question yet. I hope they never do. There's a case where they say, consider that there is the field resistances are negligible. I do have this question here, but they've never asked it, fortunately. This third one says the following results were obtained in a Hopkinson test. The applied voltage, motor armature current, generator armature current, armature resistance of each machine. Then it says determine the efficiency of each machine by ignoring the field current. So that's your keyword, by ignoring the field current and assume the iron and mechanical losses. Iron and mechanical losses are also, the iron and friction losses are equally divided between the two machines. So first, you're looking for efficiency for each machine. So that's in this specific question. I'm not going to be answering this question, but they're looking for efficiency for both the generator and the motor by ignoring the field current. So ignoring the field current, here's what happens to this circuit here. If you're ignoring the field section, then you should not have it. And there. So because you don't have the field it will also affect how you write your formulas, which means you don't have I4 there. You also don't have I4 here by ignoring the field. So even this side, I'm ignoring the field by ignoring the field. By ignoring the field. So it then affects how you sketch your diagram, even some symbols within there. So now you will then notice in the same question that they gave you a motor current and a generator current. So coming back to the circuit, in this case, your motor current then is just represented by I1 plus I2, and your generator current is I1. So even in the equations, even in your equations during the calculation, like I said, they've never asked this one before final exam. We hope they never do. So even in your formulas, there are certain things then, because you don't have the field values, then you won't need to write your I3, your I4, your I3. These is 0 because they're negligible. You don't have that whole section there. You don't have that. You don't have this whole value because it's 0. So in a case where they happen to give you such a calculation, make sure you know what to do. This calculation, like I'm telling you, it's very friendly, very simple. I hope you guys understand what we were going through, and I wish you the best. Hola.